Раз, два. Раз, два. Так. Muchas gracias. Hi. Good.
Hello.
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 Okay, we are waiting for the speaker. Turns out that's simple. Uh, Сейчас он заходит.
Слышно.
Я услышал что-то. Что вы сказали, слышно.
Да, нет, просто раньше не было слышно, нет, я поэтому так удивление
Ну,
даже
ну,
сам.
терпение нет.
Да. А
Вот
вот имеется
докладчик.
докладчик, но он выключен, по-моему, микрофон.
Все, включил.
Да.
Да,
Добрый день.
Здравствуйте.
добрый день.
Ну что, удалось найти планшет? Или за
Да,
вами
да.
нужно записывать?
Не, я нашел.
Нашел, хорошо. А доску, это самое, вы уже себе организовали или вам это самое прислать ссылку на Jamboard?
Да, я могу создать, в принципе.
Ну, как вам удобнее, нет?
Наверное, лучше джимборд создайте, да. А то как-то мы в прошлый раз писали, все время что-то там съезжало, а на джимборде там все стабильно
Скоро
пока.
Jamboard закроют.
Да, 1 октября постоянно пишут.
Есть
Ну,
даже
До
такое
первого...
стихотворение Иртеньева, что это самое, куда девалось мыло, куда оно пропало, еще недавно было, и вот его не стало. Мне надо вымыть ноги, руки, мне надо и ноги вымыть надо, верните мыло, суки, верните мыло, гады. Значит, вот с Джимбордом
По-моему, вы как-то рано начали беспокоиться. Мало ли, что еще до 1 октября у нас закроют.
Нет, но они мне недовольно, они все время пишут, и меня нервничает, я из-за этого волнуюсь. Вот
Так.
прямо пишут, going away on October 1.
А
Ам,
кто-нибудь, кстати, понял, куда можно перенести эти
Я
джимбордовские
видел,
файлы?
я пробовал некоторые доски, но, к сожалению,
сейчас.
там большей части они не размерные. То есть там бесконечная доска, и поэтому непонятно, где кто пишет. И...
Ибрагим, а сделайте еще, чтобы можно было писать другим людям. То есть, чтобы как
да. Сейчас.
на
Я
всякий случай.
поставил
А то...
читать.
Это напишут тут всякие... Это такое
Вот.
дело
Я просто
опасно.
малый там.
Не, ну если не нужно писать многим людям, то все много чего есть там.
А,
Нет,
На
конечно.
планшетах есть хорошие всякие приложения, они просто не расшаривают.
а, Так,
Да.
все,
Что
попал.
там?
Мне транслировать в Zoom демонстрацию? Или
Да,
как?
да.
Да, хорошо,
То,
сейчас. Так.
Ну, мне, кстати, не удается ничего написать. Нет, это может быть так и надо, но...
может, надо ссылку
Ам,
заново послать?
Обновить
Нет, вроде
попробую.
ссылка не меняется.
Вот я написал.
Ну, значит, это у меня что-то неправильно. Сейчас я...
Подождите, а как что-то там писать-то? Нужно заново зайти просто. А, я понял. Заново. Наверное, надо заново зайти по этой ссылке.
Заново зайти по ней,
Можно.
да?
Возможно. Сейчас давайте попробуем.
Так, где у нас чат?
Да, вот теперь я могу что-то писать, да. Вроде как сейчас могу, да. Окей. Надо заново зайти по ссылке.
Да, появились какие-то... Да.
Ну, давайте попробуем начать, только, наверное, все-таки по-английски, если это не слишком тяжело.
Сейчас, ну...
Еще Бруно тут.
Но можно
А.
говорить по-русски. Я
Ну,
все
вообще у нас
понимаю.
идея в том, что
Можно
для
говорить
записи,
по-русски, но мы
чтобы...
хотим, чтобы ты понял.
Да, да. Я думаю, я буду понимать.
No, I always say that it's possible to speak French being polite, but I know myself that it's better that other people are also polite and do not follow my advice.
Вот я
Okay,
уже
we can
знаю,
speak Dutch.
да, я уже знаю половина, что надо говорить, и первая половина я буду понимать по-русски. Если
Ну,
я
а-
уже знаю, как ты будешь говорить, я понимаю по-русски.
No,
Вот когда когда все новый, может
Да.
быть трудно, я буду спрашивать,
Okay,
говорить
no, no.
по-английски.
In fact, your Russian is much better now. I'm very, very impressed by this. But okay, so no, as you wish. If for a speaker it's exactly the same, then maybe we can speak English. But if it's really easier to speak Russian, let's try to start Russian, and maybe someone can translate if something is difficult
I can speak English, I think.
easily.
Окей.
Yes.
Yeah, then why not?
Okay, so let's start.
Okay. The original task was to build a Boolean circuit computing oh wait,
Majority of
Majority of-
several gates using AND and OR,
yes, using and or
which are in fact it use only majority of 3 gates.
yes, and that was proved by Valiant, if I'm not mistaken, and that's a famous result. After that, I used the same.
Okay, but before we switch, then this famous result, who remembers how this famous result is proven?
Okay, I can.
No, just ask people. So who remembers?
Which result come exactly?
Actually, I skip all parts of the talks when two speakers are talking. So I don't understand the question by this reason.
So which result do you mean?
That
Okay.
majority of n things can be computed by AND and OR in logarithmic depth, and
Ah.
therefore polynomial size.
I know the proof.
Yeah, but can you just say in one sentence how it's proven?
Yes, okay, of course. The statement is that we have majority. We have a monotonous circuit of AND and OR gates, and we want to compute the majority of n with logarithmic depth with a bound fan in, and I used. As far as I know, there is also a deterministic algorithm, but I used the probabilistic, so we just say that we use only mesh 3 gates to compute it to compute this, and we
Ibragim, let's try to formulate some of the theorems. I don't know, like for example, this result of Valiant that
okay.
write down that majority on n bits there exists a formula out of match free gates of logarithmic depth.
Yes,
Just
yes,
try
that's
to write
the
it.
theorem. The theorem is that there exists a circuit such that it has logarithmic depth, computing majority of n and consisting of majority of 3 gates.
Which is actually not even a formula.
Yes, it's a circuit. Yes.
No, it's a formula also, but I mean it's if
Yeah,
it's
yeah, just
logarithmic depth,
it's
you can
even a
always turn
formula.
it.
Yeah, yeah.
Yes, yes.
There is no
Oh,
fan out.
this is the result of, I mean, this is what is well known, and which is not exactly what was proven by Valiant in the beginning, but then different people, I don't know, actually Shenin Vereshchagin and somebody else noticed that you can compute, so this result actually holds. And then we can
I think
now,
it
I
was
guess,
an original paper, yeah, but okay.
no. In the original paper, he didn't use much free gate. He used, I don't know, some other Boolean function, which constant Boolean function that can be computed by constant n and or instead of much free.
Okay.
But okay, so then we can try to remember how more or less is this result is proved. Because it's, well, I guess it will be important. Maybe somebody knows already and can say how it's
Actually,
proven.
if we do not require that the resulting formula is monotone, one can prove this in another way. If you just want to construct a circuit, a non-monotone circuit consisting of and or and also not of log n depth, that's easier.
No, we can even count the number of ones.
Yeah,
Right.
but the problem is when we go monotone, right? I mean, but the construction with
No,
monotone is also
if
not
I
that
remember
obvious.
correctly, it's just the structure is very easy. We just take random majority of we take a tree and then assign the random labels to
Sorry,
to
Sasha, you
the
are talking about the proof of this theorem, which is written here, right?
yeah.
Yeah. So it's true. We just take like a ternary tree, and yeah. So we put so like that. Then again. And this is like for all of log n layers. And what we do in the leaves,
We just assign random variables to these inputs. And we say that the probability of getting one for we can see after all that the probability of getting one in the output is more than 1 minus 2 in power minus n if the probability of getting one in the original input was at least 1/2 plus 1 divided by n. And it's I don't know how it's in English, but it's like dual function. So if we inverse the inputs, so the same is true for zeros for 0. Yes.
Yeah, so I remember that there are somehow the proof is not completely trivial. First, if we go from top to bottom, and the probability to get one there is increasing. Initially, in the bottom, it's 1/2 plus 1n at least, because
Yeah.
we have more ones than zeros. And if we go, if we make logarithmic number of layers, it becomes some constant, like it crosses like something like 3/4 or any constant. And then
Yes.
another logarithm number of layers is enough to make it smaller than 2 to the minus n.
Yes, yes.
Yeah.
And
So there are two steps, yeah.
I think maybe I should write it down. So
But if you will do it for k majority and n majority, maybe we can even start with this.
yes, yes.
Yeah.
For K majorities, it is the same. The algorithm is the same. We just use some other techniques to prove these layer bounds. So the approach is the same. At first we, sorry. At first we start at the point 1/2 plus 1 divided by n, and we prove that.
Sorry, but we have to understand what is happening. You're trying to explain the in detail the proof for for k equals 3, or you're starting to do a general case. I mean, Sasha Shane also, I didn't understand. You want to consider?
No, I just tried to recall the proof for 3, and you confirmed that this is a right memory. I don't mix anything, and it's indeed the way to prove it.
Yes, I wanted to write down the general algorithm, and after that to.
But then, okay, so in the general case, let's first write a theorem that for much n, there exists a log n base k depth circuit from much k. And then that's your, I mean, that's the result new that you will present.
So you can have k here,
yes,
and then you have k here, and then you mean that this O is just not depends
Doesn't
no
depend
n and
on-
k. So it's the same for all n and k, yeah?
Yes.
Yeah, so here we have also k.
And then, yeah.
And here we have k also. So what you do, you just have k, and then you can add things, and you have k here, and you have many layers.
yes.
Yes, and the idea of the proof is the same. So we start with we take the leaves I mean, in the leaves we put random variables. So if the number of ones is more than 1/2, the probability of getting 1 is 1/2 plus 1 over n. And then our goal is to show that after all of log n's base k layers, it becomes 1 to the minus 2 to the minus n.
But
And then
we should also prove that if the number of ones is less than 1/2 minus 1 to the n, the probability comes to 0.
Yeah, but it's self-dual.
Self-dual. Yeah. Sorry. Okay. Yeah.
So
It's enough.
Yeah, okay. So the question, so now we are left with this technical problem of showing that these probabilities go in that many layers from 1/2 plus 1 over n to this 1
But
minus
sorry,
2 to the minus.
majority k is self-dual if k is odd.
Yeah. So
Oh.
that's true. Let's assume that
Yeah.
every n and k are odd here.
Okay.
That's so n and k are odd.
Yeah, there is also last step which is skipped, but if we have probability 1 minus 2 to the minus n, we can then choose, we have n 2 to the n possible inputs, and so we can choose the probability smaller than the probability of one input. So then we can fix the random choice so that it's always correct, because the union of these small sets cannot cover the entire space. So we get deterministic thing. And this is the one reason why people worry about all this, that it's not an explicit construction, So it's another story how to get explicit construction, but today we don't deal with this.
Yeah. So
So
is it clear more or less to everybody? Is there any questions? So because now now we're planning to start this, the main thing, that to show that this probability actually goes from this to that. So if there are any questions,
No,
what we
it
are
should be
doing.
clear what is the construction, how we compute which probabilities we are computing, and why the claim about 1 minus 2 minus n is enough, and how we get this 1/2 plus 1n in the beginning. So this is a very simple thing. So if it's not clear, it's our fault, and it can be explained easily. Okay.
yes, so should we move on?
Yeah, let's try to do that.
Okay. So the plan is the following. At first, we'll prove that. 1 second, I'll recall. Yes, at first we'll prove that this. 1 second, sorry. That from this point we can get to something about something like this plus c divided by 2 square roots of k, where c is some constant. It's in of this amount of steps.
Again, the constant doesn't depend on anything. It's just
Yes,
absolute constant here.
Yes. After that, we prove that we can, at this point, if we choose the right constant, we can get right to some another constant.
So now, so far in this
It is a bit
point, we are like
strange why
from
you write like this. Actually, it will be much more clear if you write 1 over square root of k of plus c.
Yes, maybe I just
square
wrote
root of k.
better
So we
to
still have 1/2, but we have now
yes.
advantage doesn't depend on n now. What is important, but it's still quite small if k is large.
Yes, and after that we prove that okay, I will then write it down in a more convenient form. After that we can get to some constant, let it be d. No, maybe I should say like this, 1 divided by 2 plus epsilon. So it's also a constant, and it's in one step. And when we are separated by a constant from 1/2, we can get to the desired 1 minus 2 in power of minus n in, again, all log of n by k steps. So this is the plan, and it's realized by applying Chernoff bounds and looking at some combinatorial
Yeah, okay, so it's k here, yeah, what, in the second line.
yes, k.
Yeah, and Chernoff bound in which steps is used?
Chernoff bound is used in
The
step
third one, I guess,
3.
no?
In
and 2 and 3 actually, I think. Maybe,
Yeah,
but
so
okay, maybe you can
so we
not.
have
Maybe you
Chernoff.
Yes.
In the first step, we compute derivatives. So another technique.
Yes. So if we explain this plan more in more details. In first step, we show that the derivative is more than more than square root of k until about this point. So from 1/2 to this point, we have derivative strictly greater than this, than square
Okay,
root.
maybe you can just, the idea is explained. Maybe you can explain in detail what you do with the derivatives, how it works, and so on.
Yes, okay.
We have to
I have
understand what
questions
function
about-
We
we
anyway
let's try
came to this point.
Yes. I forgot to explain what function are we working with and what function we take derivative of.
Yeah.
Question.
So
About 3, I don't understand. Point 3. So in the beginning there is no k, and then you use log k n steps.
Why there is k in the bound?
Yeah, but no
Yeah,
k
I was also
elsewhere.
surprised. But remember that we use majority of k elements.
Oh, sorry. Okay.
So there
yeah.
is some reason to have k dependent
Okay,
on
yeah.
k. Yeah.
yes, so
Also, if you are pedantic, you should not write these things because these are mapping of elements to element that you just transform bound to bound, which is
I mean,
yes.
come on, it's more or less clear. That's good.
no, it's clear, but just it's the wrong symbol. Okay.
Okay, we can write down the function. Let's call it phi. If we take random inputs and the probability of getting 1 in the input is p, then we can easily show that
This function is the probability that k inputs, each of them independently is 1 with probability p, will have majority 1, yeah?
yes.
So it's logical to add k here and
G for
so it's just the function which corresponds to one layer of our circuit.
yes.
If inputs are independently true with probability p, then majority will be true with this probability.
Yes. We should state here also that for simplicity we say that k is 2r plus 1. So then we can see that this function is such sum. Just binomial form. And that's it. So we have this function, and we can see that if we want to show that the derivative of this function is more than square root of k with some constant on the whole segment from 1/2 to 1/2 plus this constant. So we should just try to calculate it and see that it's true. So
Yeah, maybe
So it's a
right.
kind of a monotone function. It probably just let me draw the plane, and so it's 0 in 0, 1 in 1, and can you just draw the approximate graph of this function?
yeah, of course. It's 1 second. That's 1/2, and it's something like this. So this is also 1/2. This is it. So the more k is, the more I don't know.
Steep, крутой.
Yes, the more steep the graph is. So
So you want to say now that at the beginning it's very nice because as you claim the derivative is about square root of k.
Yes,
But then
and
it goes in the zone when the derivative is smaller, and
yes,
this is a problem. Maybe it's decreases the speed of increase, and there is a problem. But then you promise that will not happen, and you can explain it.
yes, when we reach this point, we just use Chernoff bound after that and see that we have a constant. So should I just write out the derivative or
No, as you wish.
okay,
You,
So
you
no,
can
no, no.
convince
Let's
by
ask. So
any way.
let's just ask. So what we are let's maybe first write down what we want to show about this derivative. That it is at
okay,
least square root of k times some constant on this interval, and
okay.
then let's ask if this is clear how it implies the first step.
Okay, we want to show that phi k is more than about this, like this. No, it's r, it's just 1/2 of k, so it's about square root of k for p at segment, at this segment.
So the segment that we want to quit.
Yes.
So while we don't
Yeah.
quit, we're growing in this way. So every time the difference increases at most square of r times. So
At least.
in at least by square root of r times, and then so logarithm of 1 over square root of k log. So it's even there is additional 1/2 because of square. We need only small increase like square root of k. But anyway, it's just a constant.
Yes.
Yeah.
And should I prove it? Should I write down? I just
Yeah.
No,
So
if you
now
can
let's
improve
try.
it, just explaining why it's true, it's better than writing down. But if you
okay.
want to write down, you are free to do this.
I don't want to write down. It's honestly because the whole process, because it's just making tricks with binomial coefficients, and we just I can say that if we
Just start by the idea then.
yes, if we express if we cut the same parts, and if we express it like express it as the product of other coefficients, just use basic combinatorial formulas, we can get that derivative.
No, but still it's important.
Yeah, okay.
So you
it's
have
just
many.
there is just Sasha. There is just some closed form expression for this derivative. Let's write it down, and maybe we can either do this derivation, or maybe we can believe it. I think I checked it and it's true. But okay, let's at least write down the explicit.
No, but what I want to say that there are several terms of this thing. In the derivative will be also a sum.
Yes.
So, and then the question, no, just you will need to write the sum anyway. But the question is why the sum is big? Because all the terms are big, or there is some big terms, or a group of terms that are big, just to understand the kind of how the argument goes.
1 second.
I think it's better to write something.
Yes. Okay, I'll write then. First, we can just write down the straightforward sum, the straightforward expression. So it's like this. Here I place inside the braces some terms, but I think it's correct. Here I just use the formula for derivative of product and just place these terms here. You have minus 2r plus 1 minus I x. And that's it.
Yeah, so one of the factors is we take the derivative, and the other is kept. So and there is 1 minus 1, the degree 1 smaller is taken out.
Yes.
Yeah, this
And
is
then we just use this formula. It equals 2r plus 1 divided by I c 2r I minus 1. I just use this formula, and these terms are just they just cut.
Wow.
No.
But why you need this formula? Why this c to r I minus 1 is better? It's still binomial coefficient.
Because as I can see here,
It conveniently cancels with something, or what is
Yeah,
the...
so it's
yes,
the idea is it just will cancel out now everything
Yes.
except so, and we can even write what will be in the end.
So it's better to cancel something. Let's see how it
just
works.
cancels to one term, only one term.
Okay.
I can write it, but on the next slide.
But you can copy the previous page and then erase everything you don't need, so we see that you don't cheat. And
how can I do this?
I don't remember how to copy. So Sasha, you know how to
I
copy?
will
We
copy
will-
you. I will copy your page, please.
Okay.
Thanks. You can go to the next page. It will be the same, mystically.
yeah.
1 second. So
Yeah.
All right, and then we have to erase now from the top and start.
Yeah. I can also
continue.
erase, just starting erasing, and you start writing, and I will erase everything else.
Okay. So we just place this formula, and we can rewrite it. The term that is independent of I, it's 2r plus 1. We just place it outside the sum. So it's here, plus 1 of x plus 1. And here we have sum. I equals r plus 1 to r plus 1. C I minus 1. Oh,
2R.
2r, yeah.
to r, yes. X I minus 1. Y minus x to r plus 1 minus I.
No, 2r
Let-
minus y.
To r minus y.
No, here you don't just to r minus y, because you have
No,
I
Sasha. There is 1 minus x, no?
this. I think
you want to separate them. Sorry.
yes.
Yes.
Okay.
Yes, I just separated and used this
Mhm.
formula.
Okay.
And
Yes.
let's fix. So there is this something. The binomial coefficient. Let's write it properly. So let's see. Let's do r I minus 1.
Okay.
And then here it's this.
And here we get that this just cancel. It
But
just cancel.
wait a bit. So you
Yes.
have minus the first term is just you write it explicitly what was there, and the second is
So, and the important thing what we are doing with binomial coefficient, right? We have to understand. So we go, right? It's clear what's happening. So why 2r plus 1 appears because of this formula and so on. And then everything else, yeah, it's written like it was. And here also the same. So the only thing what's happening here is this binomial coefficients that we have.
no, I am lost. So the second part is so the first part they have I in the I is cancelled, and in the second part how you just
So in the second part, we have to multiply this binomial coefficient by this thing, and then see that it equals to this times this. That's the statement.
oh, so 2r plus 1 minus I is just the last, it's just combined with this coefficient, yeah? This
Yes.
one.
Yes.
Ah. And
And we have to say that it's just this product.
Ah.
So I guess we apply the same formula, but for a different, like what's written here, but I don't know, we can even, so C2R plus 1, C2R plus 1 choose I times 2R plus 1 minus I, it's this, 2R plus 1 factorial divided by I factorial divided by 2R plus 1 minus I factorial times this. So the idea is that these things cancel out.
The
and
last term, and the first we take 2r plus 1, we take away.
Yeah. And we do something like this also in here, right? But now we have E minus 1 here and here just I. And the base of the, I mean, like but we have 2R elements choose I and 2R elements choose I minus 1.
Yeah.
Here.
Okay.
And here we can see that these terms, they just cancel because this is term for I minus 1, and it is the same as this term for I. So they cancel out, and we get only this one example of this term for I equals to R plus 1, and sample of this term when I is equal to R plus 1, but it equals 0 because C of 2R by 2R plus 1, it is 0. So after
Okay,
all,
so just write down. So yeah.
yes, so after all, we just get
I think in English it's called telescoping sum, which doesn't translate
yes,
into
yes,
Russian.
yes. I'm not really fluent.
Me too, but just I once
yes,
heard
thank
this
you.
name.
And this is it.
So say it again. What are the letters? C of 2R here is R, yeah?
R, yes.
So
It's
all
R.
letters are R.
Yes, it's all R. And here we got this. And it's approximately equal to
So now let's copy this on the next page,
yes,
maybe.
yes, I think that would be
Okay, I'm just I feel that I'm useful for something, so it's very nice,
Yeah.
nice feeling. Okay, I copy 344. You can go there now.
okay.
Where? Which page?
Oh, you copied. Oh, you copied. Oh, you changed the second one. Sorry. I copied. No, I thought you will continue on okay.
I don't know where should
Go to 3.
okay, I'll go to 3.
Yeah.
I'm
Yeah,
now
okay, so now we can erase
third.
this.
Yes. I think I should erase this. Yes.
Yeah. But it's strange. Usually, if in combinatorics we have a strange telescoping sum and everything simplifies too much, this means that there is another argument which allows us to get this answer immediately without all this computation. But here we don't see any argument.
Maybe
Yeah, I don't know.
just didn't study this a lot. I just
Okay. No, if no problem. But
okay. And we can see that it is approximately equal to r plus 1 4x 1 minus x power of r divided by 2pr, and this is approximately equal to no, I shouldn't write it here, sorry, I missed one row in my proof.
No. First of all, so you use just the formula for the biggest binomial center binomial coefficient, which is more or less 2 to the r
Yes.
divided by square root of r up to a
2
constant.
to the 2
yeah?
r, which is important here, right? 2 to the 2 r.
2 to the 2r divided by
And that's why
square
we
root
get 4.
of r, no, or 2r, whatever.
Yeah.
But
So,
then instead of 2 to the r, you write 4 to the r. Why?
because Sasha, that's 2 to
2
the
to
r,
r.
choose
Sorry.
r. So it's 2 to the 2 to the r.
r.
So it's 4. Yeah.
So one square root is deleted because it cancels with 2r plus 1. And
Yeah.
Yes, I should memorize. So this derivative, it is I think monotone on the sorry, I'm just
but why you need? It seems that everything works.
Yes.
We don't use any monotonicity. Why you are worrying about it?
No, nothing. I just wanted to reassure that if we prove it is big enough at point 1/2 plus c divided by square root of r, that implies that it is big enough on the whole segment.
No, indeed, x1 minus x is maximal when x is equal to 1/2. That's
Yes.
true.
Yes, okay.
So you can easily continue.
Yes, and here I think I missed a lot of calculations in my.
No, but I think we see, just let's look at the formula. So when x is 1/2, then this 4x 1 minus x is 1.
Yes,
And if we add some small quantity to 1/2, and then more or less we have square root of this 1 minus square root of this quantity.
it is approximately equal.
No, just square, no?
Minus-
Sasha, not square root.
Square. So
So, I mean, if x is 1/2 plus some delta, this
yeah,
thing is
plus delta,
something like 1
1 minus delta square.
1 minus delta square, and no, maybe 4, something like
Or
that.
with some coefficient, whatever.
Yeah. So if
okay.
delta is like 1 over square root of r, so this delta square is like 1 over r, and we raise it to r, and this is now some constant.
So
because
it doesn't make a problem for us if delta is 1 over square root of r.
Yeah.
And if we make delta bigger, then we start getting trouble. Yeah.
Yes. But when in fact, when we reach already the region when I have 1/2 plus 1 over square root of r, and I apply it once, then I already get 1/2 plus some constant, right? Just once, because I still can, my distance to 1/2 is multiplied by square root of r, and I already get 1/2 plus some constant, some positive constant.
Is it?
No, Sasha, I didn't say it again, or maybe you can.
So the statement is that, okay, the idea is that we have already proved, in fact, the first and the second step, I think.
No, the first is clear for me. If we take delta
Yes.
is about 1 over square root of r, then we get constant in the additional factor, and the derivative is square root of r, which was exactly what we wanted. Yeah.
So now, so then Ibragim said that this means that we reach a point 1/2. Okay, I'll write it. Sorry.
1/2
In-
plus
in-
something divided by square root
in-
of r. So it's our first step.
Yeah.
Yeah.
And then, but still here we see that derivative is about square root of r. So we multiply. So and then in one step we already get 1/2 plus some constant. Because we still can apply this bound to the.
No. We need the derivative not in this point, but on the entire segment between this point and the target point.
You think?
No,
Wait.
this is,
But,
Monsieur Lagrange did so. So we need something.
so wait. So I'm interested in the distance between phi. I'm interested in phi. So I mean, also this function phi. This thing.
Ibragim, whom do you believe? Do we need Monsieur Lagrange or not?
I'm not sure. I just I
No,
just
Sasha. Look, I think we don't need
Yeah,
Lagrange. I
okay.
mean, because now, well, look, I'm interested in this difference, right? Like applying phi
Yeah.
to 1/2 plus 1 over square root of r minus phi of 1/2, which is 1/2 also.
Yeah, and
I
this should
need
be
derivative
in the
this and
square
this.
brackets. We have derivative of phi in some intermediate point.
Yeah, but between this 1/2, but not in the, not in the interval between the images, between the inputs. No?
Ah, yeah. You're right. I'm stupid. Yeah.
So now I think more or less we have proved that in log n base case steps, we reach the point where we have 1/2 plus some absolute positive constant. And then the
Yeah.
question is, are there any questions about this part?
I have a question. So
Yeah.
when we start to define phi k, it was defined to be a probability, but then we forgot to normalize. There was factor 2 to the minus 2r plus 1.
No,
So
where we
we-
forget to normalize. Just show the previous slides.
Yeah, just the first place where we have phi
Ibragim,
k.
can you show the previous slides? Then
Yes.
Bruno will.
Okay, I think this is the
Yeah.
Yeah. So there is a sum. Oh, sorry, no.
There is
okay,
P.
I was stupid
When P is
again.
1/2, it's a normalization
yeah,
at
sorry.
1.
Okay, yeah. Sorry. Okay, everything is right.
Yeah.
Okay, I guess I used there was no need for Chernoff bound in step 2. So should we now go to the
So you want me to make a copy?
I don't know.
Or maybe you don't need a copy, you can just take a
I think we don't need the copy. We need, let's now start proving that from 1/2 plus some positive constant, we get to 1 minus 2 to the minus n, again, in this log n by
Okay, so we
base.
go to the clean page number 5 and
Okay.
do this.
And here I think there was a strange complex proof in my template, and I think Alexander wrote it in a simpler way. So if we apply Chernoff
Okay.
bound, 1 second.
Let's try it simple way. We don't need a...
Yes, sorry. I just
So now we have probabilities 1/2 plus 1 over square root of r, and
Yes.
you should
No,
get
it's
1
already
minus
1/2 plus constant.
yes.
1/2 plus constant, yeah.
We are now
Yes, sorry.
now in 1/2 plus epsilon.
Yeah.
And we want to get to 1 minus 2 in power of minus n.
Yeah, so it's constant, we want it exponentially small.
Yes. So we have, if we had a, if we had, let's say we had not epsilon, we had not epsilon, we had 1 minus delta. So
And delta is smaller than 1/2 now.
yes.
Yeah.
And we need to prove that
But it's strange, we still have your nice formulas, which are completely exact, and then you switch to Chernoff bound. And it's not even clear how we will apply Chernoff bound.
Why it's not clear, Sasha? Because it's like we have now a random variable that takes, I mean, with probability significantly larger than 1/2. And we're interested in the probability that majority of them is larger than 1/2. I mean, that the majority of them is true. That the majority of them are 1.
So you apply Chernoff bounds to just k variables, yeah?
Yeah, to k variables, and we have to say that, I mean, if on input we have a number larger than 1/2, then in the output we get something which is closer to 1 more and more and more and more.
But is it valid for all k or only for large k?
I mean, Chernoff bound is valid for all k. We will use some Chernoff bound. There's just some explicit formula that is, let's see.
Yeah.
yes, here we just use Chernoff bound to prove it, because the distance to the point 1 is actually the probability of getting 0. So we just prove that by applying several times this function mesh k, we get to it fast enough and
Okay, maybe if you write Chernoff bound, it will be easier for us. We will look at something and then we will see something.
yes, it's just the probability of okay. I'll just write down from the messages. X is less than or equal to p minus epsilon it is it is equal to second no it's less than
No, it's most.
2e in power of d of p minus epsilon p and like this.
So it's not enough to use the standard Chernoff bound with minus 2 and epsilon square, and you need this strange Kullback-Leibler distance.
No, I mean, I think it's more or less standard with the Kolmogorov-Seminar distance. I mean, that's the way you obtain.
Still, just 2 and epsilon square is not enough.
I think. Wait.
If it's
no,
enough, then
because...
maybe it's easier to look at it, because now we have to estimate this Kullback-Leibler, which is also quadratic over epsilon. So why you don't, if it's quadratic over epsilon is okay, why you don't like 2 and epsilon square?
No, because Sasha, we want this Kullback-Leibler distance to actually go to infinity. So, okay, like in our case, well, what is n? N is k, right? We have k random, k random variables. Then pi minus f, so pp is the 1 minus delta, right? It's the probability that one of them is that each is 1. It's a probability 1 minus delta.
Yeah.
Then pi minus epsilon is what? I can ask somebody for understanding.
No. Pi is a bit bigger than 1/2, And pi minus epsilon is still probably you need bigger than 1/2.
No, I mean, we are interested if p minus epsilon is 1/2. We are interested, so we have k random variables, each taking the probability 1 minus delta. We are
Okay, all
interested
right.
that in the error probability that majority of them are 0.
It's better to have it's infinitely smaller than 1/2, but infinitely bigger. But okay, it's 1/2. Okay.
No, I mean, if k is odd, it's enough to I
Okay.
mean to
Yeah.
count the probability that
Yeah.
most 1/2.
Yeah.
So now what happens with delta? We had delta, and now we get, it's like the 1 minus our probability of getting 1. And now delta becomes e minus this thing. In one step. So, or in other words, log 1 over delta becomes this distance times k. That's why it's not enough to use just square. Because now...
No, I didn't understand. Logarithm of 1 over delta is big. And,
yes.
You want to make it even bigger.
Now in the beginning, we are actually looking at the logarithm of 1 over delta, right?
Yeah.
We want to show that it reaches n weekly. Basically our goal that now it's some constant, and we want to show that it becomes equal to n in log n base k steps. And for this, we show that it's multiplied each time more or less by k.
Yeah.
So the only thing remains is to show that this is at least some constant times log 1 over delta. So that what happens with log of 1 over delta each time is that it gets multiplied by k. That's times some constant.
And if we did this, we get something like epsilon square, which is not enough because
which is bounded. This thing has to grow with delta, right?
Because goes to 1. Yeah, 1/2. Ah. Mm-hmm.
Well, let's just try to understand this. Why this last thing is so.
Why this distance, Kullback-Leibler distance, is large?
Yeah.
Okay, why it's large?
Okay, let's try to
It's
write.
a
So if you have
constant. 1/2 and 1 minus delta are constants. So this Kullback-Leibler is also constant.
No, we write how the delta changes. We assume that now probability is 1 minus delta, and then we say that the probability is 1 minus delta prime when delta prime is equal to this.
Ah, yeah, I see.
So I think the formula is like that, right? And now we get, in our case, we get this. So it's like 1/2.
No, I'm afraid you mixed the interchanged x and y in Kullback-Leibler.
Do you think? That's
because
important.
to prove Kullback-Leibler, we compare the probability according to standard measure according to shifted measure. And shifted measure is pi minus epsilon. And so optimal coding is used according to shifted measure, and we compared it with normal coding computed with. And so I think x ln x should be for shifted. Oh, no. Maybe it's okay. Yeah, sorry. Sorry. It looks okay.
It's symmetric. in
No,
fact.
it's not symmetric.
No, it's not symmetric.
This is the problem.
So the formula should be like that in our case.
I've put it in the chat, the formula from Wiki, so it's right.
But you don't put anything in the chat because at least I
No,
can
I see.
anything.
No, it's in the chat. Yes.
Yeah. Okay, then I am somehow.
No, I mean the other thing is to believe that these guys are also in that order here, right? But it's also from the wiki.
Yeah. Okay.
No, and then I think more or less then look, then it's more or less clear that this thing is log 1 over delta times some constant, right? Because it's a major, I mean all the other things are constant and this grows. No? This expression one half. So the first thing is like some constant in the first term. The second term, well, it's log 1 over delta and again some constant. When delta goes to 0 is a case.
No, so say it again. So we started with logarithm of 1 over delta. And now we want to get something bigger. And why do we get something bigger?
Because we also have this k.
Where we have k?
No, because in the Chernoff bound we have this Kullback reliable distance times the number of variables that we take majority of. I mean, in the number. So when we consider log 1 over delta, what happens is that it was log 1 over delta, and now it becomes Kullback-Leibler distance times k. And Kullback-Leibler, so we want to show that it's more or less k times log 1 over delta. And to show, but instead of log 1 over delta, we have this Kullback-Leibler distance, but then we only have to observe that this Kullback-Leibler distance is more or less log 1 over delta times some constant.
Times some constant, constant 1/2. Yeah?
Yes.
Why constant 1/2?
But it's just 1/2
because there are some negative
logarithm.
terms, no? Maybe. Or
no, what I'm saying that if we have k over 2, it's not enough for us because.
Why?
I don't know. If k over 2 is okay, then yeah. Yeah,
I mean, potentially the only problem can be here is that for some, well, depends what's the constant here.
Which constant?
But I mean, for all large enough k, this argument works, no? Because there's some universal constant c.
No, but why cannot we write just that this is greater than the second term, which is 1/2 log 1 over delta? Isn't enough or not?
But I mean, I'm not sure that it's true because there are some negative terms. I mean,
which is negative? The first one is negative.
Well, so but we have log 1 over 1/2. It should be negative, at least this thing, no? And then this first term is
yeah, it should be at least. No. The first term. Sorry. So this should be also minus log 2.
Yeah, I mean, we know definitely that this thing is strictly positive for delta less than 1/2. When delta goes to 0, this thing grows like log 1 over delta. So definitely for some delta larger than 1/2, sorry. So okay, so we have this thing, I guess. This function. We have this function here. So we are interested in the value. So we are so there is 1/2. Now delta is like 1/2 minus some constant, and we are interested in the behavior of this function when delta goes to 0. We want to show that on this interval, this is at least some constant c times log 1 over delta, right? And I mean,
so this function, so
well, at
can
least
we
when
show?
when it goes to 0, it grows like 1/2 log 1 over delta minus something constant. So at least, I mean, starting on some interval, it's at least, I don't know, 1/3 of log 1 over delta, right? Here.
So how do you see this?
Well, I mean, Sasha, look. So look at this formula. The only thing that goes to
Which
so this in
formula?
fact goes to infinity because of
Yeah.
delta when delta goes to 0. But everything else is constant. So I don't know. I have 1/2 times 1 minus delta, which is
So
1.
we don't need log 1 over delta. We just need some constant here.
Yeah, it's not.
Yeah.
Yeah. So I mean, on some interval here, I guess this is at least, I don't know, 1/3 of log 1 over delta.
Mm-hmm.
And between, we have to say something between this and this. And I guess I can just
Because
say
it's
that
just
this,
constant number of steps if we have any constant.
yes.
If the no, actually, when k is bigger, the step makes greater improvement in probability. So even for k is equal to 3, we get after some constant number of steps, we get something close to 0 because it's just some function which decreases and converges to 0.
Yeah.
For bigger k, it's even better.
Yeah. Well, we use the bigger k. We need k. Because we want to show that it converges in log n base k
Yeah,
steps.
but
So
this is for the last step when we switch to smaller constant to 1 over 2 to the minus n. At this stage, it's important that we are going faster.
Yeah.
And in the middle stage, it's enough to have some finite number of steps, which is finite and bounded, uniformly bounded, I guess. No, it looks a bit like a patchwork. We use different arguments and different steps. Still, we consider just one specific sequence and try to estimate the speed of convergence in this kind of 3 stages, which is a bit ridiculous.
But I mean, this the same was happening in the original Valiant. But in the
yeah,
original Valiant, just because we have an explicit function. In the beginning, we say that it goes,
yeah,
decrease,
yeah,
the distance
yeah.
to the half is decreased by some constant because just derivative at 0 is strictly
Yeah,
larger than 1.
That's true. But
So here, instead of this, we had to compute this derivative explicitly. So for some reason, we have a telescopic sum, and we can obtain a bound, and it's a good
for
bound
some
for us.
mysterious reason,
And then again, but then in the second step, we wanted to show that each time the distance to 1/2, like more or less, gets squared. Well, or in terms of logarithm, and it gets squared just because it's like derivative is 0, so it's more or less
no,
like the
it
second
depends
term.
actually. It depends actually on
And
depends
here we
on
have
k
to,
somehow. So we need. So what you say? But just a specific question. So you have this function like this. Remember our picture. So this here derivative is square root of k, and here the derivative is 0. But what is the second derivative? Do we know?
the second derivative, well,
The idea is that the bigger k is, the function
I guess
grows faster.
there should be now, Actually, of the cave derivative, there's more or less only non-zero. I guess more or less something like that. Because
so you think
because
that
delta,
this
it
is
was
just
delta, and now it becomes
proportional
delta
to
to the k.
1 over delta to the k if it's delta, yeah?
Yeah. Well, just delta to the, not 1 over.
Yeah,
I mean,
not
like
1. Yeah,
distance to 1 was delta, and now
yeah,
it
yeah,
becomes
yeah,
delta
yeah.
to the k.
Delta to the k.
So I guess another way to try to show this would be to write. But on the other hand, so the point is that we have this Chernoff bound that is just true.
K, that's omega of k, what we want really.
Yeah.
So somehow Chernoff bound is just proving how this function behaves in near zero. And indeed, it's logical to use Chernoff bound because Chernoff bound is exactly about this function. And here we use derivatives, and here we just say that we can cover with O of 1 steps this distance, because even with fixed function corresponding to k is equal to 3, we can cover this in O of 1 steps. So this is the reason why we use different arguments in different places, because both Chernoff bound and derivative works okay close to the end point, and we don't know what to do in the middle, and we just say that finite number of steps is enough.
Yeah.
Okay, so I think we just everything is very now more or less clear what we do, and it's very. But there was an announcement. You said something about that something is optimal in just which I didn't understand at all.
Yes.
Yeah, so that
Something cannot be improved for some reason, but what cannot be improved and for which reason?
There is a lower bound for the circuits, unbound funding circuits that, oh no, it's not O, it's omega. Its depth is omega of log n divided by log n. But here we can see that if there exists
No, but where is k? Or it's bound
sorry, Sasha, that's another thing what's happening. We are now considering another problem. We want to a circuit for majority function.
Yeah.
Unbound, just an ordinary and or circuit, but with unbounded funding and polynomial size.
So it's
So we have Razborov Smolensky, for example, or something like that, to show that it's not impossible to do in constant depth and polynomial size, right? But in fact, if you look with the size is polynomial, what is the lower bound on depth? It's log n. It's not just log n, it's log n divided by log n.
Yeah.
An observation is that there is the size is polynomial and the gates are unbounded Fanin. So not just 2. Not just Fanin 2. The observation is that with this result about much n for much k, we can show that this bound is tight. So we can construct a polynomial size and depth log n divided by log n.
So we want to show not that our bound is tight, but using this construction, show that the bound for majority is tight.
Yeah, I mean, well, our bound. I mean, this bound about much n from much k. I mean, it's tight because it's just if it has to be def log n base k, because otherwise.
Because there is not enough inputs. Yeah.
Yes, and that's it. We just apply that bound that there exists a circuit with depth of log n divided by log k, and if we take k equal to log n, then we see that from the one side we can implement this circuit by just iterating over all subsets of size k half. And for the other hand, this is a constant depth polynomial size circuit that is computing Maj k, and then we can compute Maj n using only majority k gates with a circuit of depth log n divided by log k, which is in fact log n divided by log n.
But just I'm sorry again. I'm kind of stupid. I've lost everything. So can you repeat again what Sasha explained about Razborov and Smolensky and all this?
Yes,
Just say it again.
we have a lower bound for monotonous circuits computing Maj n unbound fan-in. It is log n divided
Not
by
necessarily even not
well, yes,
necessarily mono.
okay, or and or gates.
No, but with negations or not?
Is there a negation or no? I don't remember.
Sorry, what's the question, Sasha?
So negations are allowed.
Lower bound works against formulas circuits with negation. Yes. In
With
the upper
negation.
bound, there is no negation.
Okay, so
there is a polynomial size circuit of bounded depth.
yes.
Unbounded fan-in. You can
unbounded
and
fan-in.
or can receive arbitrarily many inputs. The size is polynomial.
And so this we assume as given one. So this is we don't want to get a new proof of this.
No, it's Razborov-Smolensky.
It's Razborov-Smolensky. We don't
gives us
So Razborov and Smolensky,
every polynomial
the lower
size
bound for the
circuit for majority has to have depth log n divided by log n in unbounded fan-in model.
And now you claim that there is a circuit, such circuit, which match whose depth is exactly log n over log n, right?
Yes.
Yeah. And for that you construct it using your construction and a trivial construction, a trivial monotone construction of majority k by just taking all the disjunctions.
Yes. So we get Maj n from Maj k of depth log n divided by log n, but then each Maj k we can construct instead of depth log k, we can compute in depth 2, just because k is log n, so we can use exponential size formulas for each Maj k, exponential size d and f, but now this exponential size is polynomial size, so that's fine. I don't know if
for this
was observed somewhere or not.
For this we use the property of this U construction that we use is not that it's monotone. It's just that it's no.
Well, I mean,
I
don't know. I mean, as a result, we get a monotone circuit, if you will. But the most important thing that the depth is log n base k. So we save log n by applying this for k equals log n, so that now each Maj k that efficiently you can compute this Maj k by log n depth. So the idea is that now we can use exponential size formulas for each Maj k, because it's like scaled down. So now it's polynomial for us. So instead of log k, we can get 2 each log k. So in the end, we get log n divided by log n.
Yeah. And this was not known, or this was proven in a different way.
Maybe it was known. I will have to check. I don't know actually.
Yeah, indeed, this is nice argument, but it should be checked what people did about this before.
I think, well, it has to be checked, yeah. This thing with much n from much k, I guess that wasn't known, at least. And the fact that it also gives this nice and very simple application, then it's also nice. But it's interesting on itself also, I think, that you can generalize Valiant's construction. For example, I think it's open, so it shows that there exists a, log n base k formula, formula for much n from much k. There is open if there exists such a formula and efficient, deterministic polynomial time computable. For example, we know this for that there existed for when k is 3, but not for general k.
And if we use the sorting constructions, sorting networks, it doesn't help much, because
Yes, but no, that's true. So in fact there is a construction of a sorting network that uses what they call comparators on k elements,
yeah,
but
of depth log n over k, or not?
depth log n divided by log k, or log n base k.
Yeah.
But the point is that we can like in general case, it's so for example, if k how to simulate every comparator with just much k if we don't have constants, for example. So the non-trivial question is if you don't allow to use any constant like 0, 1. So here in this construction we don't use any constants, right?
Yeah.
So how then it's not clear, then you cannot express all the things that, comparators, you have to express what's the minimal element, the second minimal element, the third minimal element, and so on. And here you
And
have
normally
just
you do it by adding constant.
normally I'm doing this by adding constants. So this implies that if I had constant, then I could do just majority k, I can construct a circuit.
So for example, the middle element of three, how do you compute?
The middle element of 3.
Middle element, you have majority of 3.
Well, it's
How you
majority.
compute the middle element?
Middle element is easy. It's a majority, just the middle element is a majority.
Yeah. And maximal
Okay,
element?
so like the minimal element, I guess you have to run majority. Well, you need probably majority on more than 3. It's like, for example,
Okay, no, if it's more difficult, that's okay. Yeah.
no, the idea is that basically, well, if you had zeros, and then you're applying majority to the rest of the inputs, you are basically asking if you are basically moving your threshold to the 0, right? If I run,
So you need to add three zeros or 2 zeros or get majority to get minimum element. Yeah. But then you need a bit more elements, but still twice more. So it's not that difficult. Yeah. Okay. So it seems that's we more or less clear that that's just a kind of getting that you can get from Valiant argument in a very nice way. But one should check whether maybe somebody noted it already. But it looks natural, so maybe somebody were doing this, but anyway, independently of this, it's nice. Okay, then we should thank the speaker, and for the next time we have, as planned, we have a talk of Gleb Novikov, who will explain kind of statistical analysis of mixture of distributions. So we have several distributions, and we have sample mixed sample.
Sasha, it's terrible. Sorry. Somehow you create a terrible noise. I don't know how it works.
Terrible noise.
Now it's okay, but before that it was something fantastic.
Yeah. So Gleb is even just now he sent me a abstract. So I will put the abstract in chat without, instead of trying to. Oh, your message is too long. Okay. Let's try the first half. Yeah, first half is okay. And the second half is. The second half is here. Yeah, and do we have other potential speakers for the day after?
So in principle, there are some results from people from here. The idea is about, we want to study some properties of infinite graphs. That's Valentino and other guys, for example. For example, how to check. So we given a graph, infinite graph given by a Turing machine, how to check that it has a Eulerian cycle, for example, or something like that.
Infinite graph. And this just in terms of kind of recursion theory, how complicated it is in terms of
so
hierarchy.
how it's usually it's like easy when you can solve it with just a halting problem, because without halting problem in this thing you cannot do anything.
Yeah.
But sometimes for some problem it's so it's easy when it's in P1. But it's hard, like.
But they study
it's
Weyrauch degree or something else.
Sorry?
They study Weyrauch degrees of this or not, because this can
No,
be.
well, I don't know what is this.
No,
I know that probably
there are some results like Ramsey theorem, which says that if there is given some infinite object, there are some another infinite object inside. And this existential theorem, one can be reduced to other, which is called Weyrauch degrees.
No, I don't think they just in terms of this arithmetic. How it's called, arithmetic hierarchy with computable things.
Okay, this is also possible, but usually it's strange that they don't do Weyrauch degrees. But
Can you write it down, how at least how it's spelled, so that I can send them?
Okay. I will write on the page 6.
Okay. Weyrauch.
Okay, but I can even type, yeah.
Weyrauch degrees.
Oops, no, sorry. No, it's very interesting thing actually. Okay, no, it's not Weyrauch by Weyrauch, sorry, but it's very well known thing. So the idea is that, for example,
No,
again noise.
terrible.
Terrible noise.
you have, well, now try to continue. At some point, you get like a very robotic sounding voice or something like that, like
Okay, strange.
you are using autotune or something.
Strange. Okay, what I was saying, just let me try to advertise a bit Weyrauch degree. So, for example, there is a theorem that every continuous function which changes the sign has a zero. And this theorem can be considered as a kind of a task. Given a function, continuous function, it's a kind of a point in a space. Compute the zero. So, and there is another theorem, for example. Find a fixed point in a mapping for a segment to to itself.
Yeah.
And this theorem is somehow reduced to the first theorem. Because
I don't
take
know.
f
Yeah,
of x
maybe, but
minus
I don't
x.
understand. The point is that they are considering like algorithmic problems. I'm not sure that it's a.
No, now,
So it's just
no, that's okay. So first of all, you transform what this is a reduction. Reduction is you transform the function f to function f of x minus x. Is a computable transformation. And then the answer, you get back the answer for the original problem. So somehow it's not much more difficult to compute for a computation point to compute the fixed point if there is an oracle which computes zeros. And one can ask the same, for example, for Brouwer theorem for 2 dimensions. Imagine we are able to compute the fixed point for 1 dimension. Using this as an oracle, can we compute fixed point for mapping of a square to square? And this seems to be more difficult problem. So there is a notion of reduction in this sense, computable reduction. Between the problems about infinite objects, there is still a computable reduction. We transform computably the given object, then apply the oracle, and then transform back
how's the object given? I don't understand.
no, there is a notion of a mapping, of a computable mapping from one continuous space to another continuous space.
Yeah, yeah. I don't understand.
And
Yeah.
so it can be defined in different ways, and there are different notions, but this is what is Weyrauch problem. So, for example, there is a classification. There is a Ramsey problem. If you have a coloring, you want to form a uniform subset. And there is entire classification. The more colors we have, the more difficult is the problem. Or sometimes we have n colors and want to find only k colors. So it's a huge domain when people classified a lot of things. So what I'm suggesting that Valentina also explains how his results are connected with what people were doing in this Weyrauch degree story. So, for example, a great expert in Weyrauch degree is Rupert Hölzl, which is, I can even write it, Rupert Hölzl.
But Valentino knows him very well.
Yeah. So probably they are. Probably Valentino also knows about Weyrauch degree. Just my request is just to clarify the connection between this. Of course, there is a way to show that something is not reducible in Weyrauch degree by showing that the algorithmic complexity of one is more bigger than the algorithmic complexity of another. But I guess it's not the only way to show this.
Well, okay. So at some point, I guess we could have something like that.
Yeah, but just in 2 weeks, more or less.
In 2 weeks, well, let's see. I don't know. I'll try to maybe not 2 weeks. I'm not sure that we could
Okay,
have
just
him, but
ask. Maybe our today's speaker can also explain something else, because it was today it was very nice, and why you have if you have something else to explain.
so
would you
we
find-
think so now we have a nice observation. So he made, I mean, about approximate majority. Approximate majority is when the number of input bits is a fraction of ones is bounded away from 1/2 by some
Yeah.
epsilon. So, for example, it was known that approximate majority is in AC0 in depth 3, in fact, when this thing is some constant. You know, epsilon, the distance from 1/2 is some constant.
Mm-hmm.
So, and Ibragim proved that it's also in AC0 when it's any reversed polylog.
Mm-hmm. So AC0 is just bounded
Constant depth,
and polynomial
constant
size.
polynomial size. Yes. So I think it wasn't known. So he showed that he observed more or less, in fact, using this idea that it's also in AC0 when epsilon is 1 over polylog of n, and for any polylog of n. An interesting question is whether it's tight. I don't whether it's in AC0 only when it's also like 1 polylog of n. But I don't know.
Да. Но это самое, нет, это вы рекламируете докладчика, а докладчик-то сам что, он хочет про это рассказывать или как?
Ну,
Вы как-то так
я
сидите, как
могу,
будто...
я могу рассказать, просто это тоже довольно, не знаю, прямое, ну, плюс-минус прямым образом получено из вот того, что Мажен Машка, то есть там оценка вида log эпсилон делить на log n получается для глубины. И там получается, что вот для 1 делить на n это получается log n на log n опять, а для полилога
Нет, так
получается...
может вы тогда еще заодно объясните, как, я не знаю, это же не все знают, как это
Не
approximate
все,
majority.
я...
Вам же для того результата нужно, вы применяете approximate majority для констант.
Ну да. Ну, я
Нет,
могу...
вообще, если
можете-
вы что-нибудь объясните такое, что вы знаете, то, скорее всего, окажется, что другие этого не знают, и тоже будет хорошо.
Вот, так идея может быть, что вы расскажете про это approximate majority для константы, который там кто-то как-нибудь доказал.
Мгм.
И потом еще объясните, что можно из этого получить для обратного полилога тоже там, например.
Хорошо.
Если-
Это когда?
Нет, ну просто если это вас не напрягает особенно,
Да,
то-
если это,
Не, не
Нет,
я не
напрягает.
знаю,
Ну,
то
вот
есть это не супер обязательно, я не знаю, как там у вас сейчас.
Нет, вообще здесь ни о чем речь нет. Ну, просто...
Да.
Если вам самому вы не очень травмированы сегодняшним опытом и готовы его повторить, то почему бы и нет?
Да нет, я готов, просто у меня опыта раньше не было, поэтому
Нет,
как-то...
но в этом также некоторый смысл может быть для вас, что вот на вас нападают, а вы привыкаете к этому.
Ну да, но мне интересно, я бы хотел.
Да. Ну давайте, тогда, значит, в какой-то момент, вот, ну, в зависимости от того, что там Саша договорится с Валентином, а может быть вы тогда...
Да, ну условно через 2 недели, подождите, а что у нас, значит, на следующей неделе у нас
На
Глеб,
следующий у нас Глеб.
вот, ну, может быть, через...
Я помню, что были разговоры, что в начале мая семинар нельзя устраивать, потому что никого не будет.
Но потом Верещагин сказал, что в конце концов, что 29-го можно. Я не знаю, как насчет следующего раза. Ну ладно, с Глебом мы уже договорились, в общем, так что пусть уж он будет, что будет, то будет. А следующий уж вы тогда смотрите, Саш, и Ибрагим,
Да.
как вам удобнее. Если вы там куда-то соберетесь, там, я не знаю, кататься на байдарках в майские праздники, то не надо это отменять из-за того, что мы хотим делать доклад. Но если, так сказать, вы можете, то why not?
Да.
Ну,
Хорошо.
хорошо, тогда будем...
Хорошо,
Всё,
спасибо
тогда
тогда еще
пока.
раз.
Да,
вам
спасибо.
за доклад. Да.
До свидания.
Мгм.
Хорошо
Пока.
получилось. Все, пока.